Good evening, everyone, and welcome to the Geological Society. I'm Richard Hughes of the Geological Society, and it's my pleasure to introduce this evening's speaker. One of the first things I was going to say was, would people please ensure their smartphones are turned off? Thank you for the gentle reminder, whoever that was. In addition to making sure your smartphones are turned off, just one other housekeeping announcement this evening. At this time on a Wednesday evening, we have no practice fire drills scheduled. So if you do hear the fire alarm, you will need to evacuate the building. And for those of you at the front of the auditorium, it's through that door on the right, follow the green illuminated signs. If you're right at the back, you need to go back out onto Piccadilly and muster in the Burlington House courtyard. So before I introduce the speaker, just a little plug for one of the displays we've got in the lower library, which we hope you'll take a look at later on. Last month, in May of this year, we marked the 100th anniversary of the election of the first female fellow to the Geological Society in, what was that, 1919. And as part of our centenary anniversary programme, we have brought the Raising Horizons photo exhibition back to Burlington House. It's just next door there. And we've also got a small exhibition on early women geologists. So please do take a look at them after the talk. But on to the main bill for this evening. A little bit of introduction about subduction zones. These, of course, as I'm sure you all know, occur where one plate slides beneath another and are known for generating some of the largest earthquakes that we've experienced on Earth. Many of these are also the cause of tsunamis, as we all know. We've recently discovered that some of the faults along subduction zones also experience periods of movement that don't generate felt earthquakes. And despite not being sensed at the surface, these slow slip events, as they're called, may have the potential to trigger highly destructive earthquakes nearby. This evening, we're going to be learning about efforts to understand movements along the Hickey subduction zone in New Zealand. Slow slip events are common along the northern part of this Hickey subduction zone and occur at depths that can be studied by seafloor drilling, seismic studies and near-surface monitoring. Dr. Rebecca Bell is going to be describing efforts to characterise and understand this fault system, and she's also going to be telling us about some of the early results of her research project. Rebecca's the principal investigator, the PI, on the project which is known as the, correct me on this one, Rebecca, please, the NZ3D FWI project. I'm sure you'll explain what that means. And Rebecca's a senior lecturer at Imperial College, London. So, Rebecca, thank you, and over to you.
Okay, thank you very much. Okay, well, good evening, and thank you all very much for coming to this lecture. So, over the last 15 years or so, our understanding of how the largest faults on Earth slip and behave has really been revolutionised. And this has largely been due to developments of technology, but also the rather strange behaviour that some recent earthquakes have had. And these things have really challenged us to stop and rethink our understanding of how the Earth moves. And in some cases, we've had to go right back to the drawing board in terms of our understanding of how faults slip and rethink things that we thought we knew and understood. So, my microphone kept falling off in the next one. Hopefully it won't this time. Our understanding of fault slip still leaves a lot to be decided. We've still got a lot to learn. But over the last few decades, there have been some really exciting recent discoveries. And we've learned that the Earth moves in a completely new and unexpected way. So today, I feel really honoured to get the opportunity to tell you about some of those recent discoveries that have been made by scientists around the world over the last couple of decades. But I'm also really excited to tell you about some of these new experiments in New Zealand that me and my colleagues, some of them who are in the room, have been involved in, both on land and at sea, to try and unlock the secrets of how faults slip. So, unfortunately, we have the first clip. Over the last 15 years, there have been a number of very large earthquakes. In 2004, there was the Sumatra Andaman earthquake, which was a moment magnitude 9.1, and produced a devastating tsunami, which killed over 220,000 people around the Indian Ocean. And I think this event came as quite a surprise to people because we hadn't seen events as large as this since the 1960s. And I think people had kind of forgotten that events like this can and do occur. If we could move on to the next step. So unfortunately, we didn't have to wait very long until the next very large earthquake happened. And that was in 2011, the Tohoku earthquake in Japan, which was a moment magnitude 9, also produced a devastating tsunami, which killed almost 20,000 people, and also caused a nuclear accident at the Fukushima power plant. Thank you very much. Next slide. So since the 1960s, we've known that the brittle outer part of the Earth is divided up into a series of tectonic plates that are all moving and interacting in different ways. So those plates have the same properties as this digestive biscuit. Other biscuits are available. In that, they're brittle. So when they interact, all the deformation and the cracking in the earthquakes, or these crumbs I'm making, they're coming from the edges. And the interior parts of the plate tectonic biscuits stay relatively deformation-free. So in some places, those plates are moving apart. So I'm recently renovating my kitchen, so I have lots of bricks lying around. They're very useful to use as plates. So in some places, those plates are moving apart. And very famously, that's happening in the middle of the Atlantic Ocean. And every year, we are moving a few centimeters further away from North America. But extension is also happening on, saw some people very disappointed. Extension is also happening in some places on land. And on one area where that's happening is Greece. So if you take a look at a map of Greece, you'll notice that it has a hole in the middle. Oh no, sorry. Women's clothes are really not designed for microphones. Okay, so if you look, it has a hole in the middle. That's the Gulf of Corinth. So that's where I did my PhD. It's where my kind of geoscience career started. So what's happening here is the Peloponnese is moving south, and it's ripping away from mainland Greece. And when continental crust extends, cracks develop, which then grow into faults. And this is what faults in that extensional setting look like. So what's happened here is that we've had a stack of limestones, which have extended. Cracks have developed. They've grown into a fault plane. This block, which has the road on it, has moved down relative to the block on the right, and it's exposed this fault surface, which is this kind of nice shiny surface that you can see here. So the key thing in terms of seismic hazard is to know that as a general rule of thumb, the larger the fault, the larger the earthquake you can have on that structure. So the key parameters that we're interested in are the length of the fault, the kind of height of the fault, the area over which we can have earthquake rupture, and the displacement, the amount that those blocks move. So I'm confident that everybody here has heard of the Richter scale, which is a scale used to measure the size of earthquakes, and it's based on the amplitude of shaking. Oh no, I shook too much. My apologies. Next time I'm going to wear very different clothes. Okay. And it's based on the amount of shaking detected on seismometers a particular distance away from the earthquake. A more modern way to measure the size of an earthquake is the moment magnitude scale, often written as MW, and it's related to the area of the fault that slips. So some of the biggest earthquakes that we've seen in the Gulf of Corinth area recently occurred in 1981, and they occurred on faults which were 15 kilometers long, 10 kilometers deep, and involved displacements of 1 meter. So I should have said that big fault plane you see is not the result of one cataclysmic earthquake. It's the action of many, many earthquakes over time, each of them perhaps with a maximum displacement of about 1 meter. And that produced an earthquake with a magnitude of 6.7. So earthquakes on faults like these can be very destructive. So it's these types of earthquakes that failed in the recent Italian earthquake sequence that was deadly. So these can be very dangerous, but they're by no means the biggest faults on Earth. So in other places, the plates slide past each other. And this is very famously happening at the San Andreas fault. When that happens, the boundary between the two plates is called a transform fault, and they're often vertical or subvertical. These faults can be really, really long, and there's a good example of it in New Zealand. And as we move through the lecture, New Zealand will begin to be our focus. So this is a first look. So this, oh no, bear with me. I did try this kind of Madonna-style headset, but that didn't work very well either. Okay, so this is a satellite image of the South Island of New Zealand, and we're looking across the North Island. So the calling card of faults in the landscape are very sharp changes in elevation. So if we look at the bottom of the image, we can see these snow-covered mountains, the Southern Alps. And if we move to the west, very quickly and abruptly, we go to this low-lying relief, almost across this kind of knife-edge transition. And it's pretty easy to draw a line through there, and that is the Alpine Fault. So geologists have studied the composition of these mountains and this high topography here and found they're one of the same. So at one time, those areas were connected, but it's been displaced many hundreds of kilometers. So this fault is a biggie. It can experience magnitude 8 earthquakes or greater, but it's, again, not the biggest fault on Earth. So the dubious honor of being the location of the largest faults on Earth are zones where plates collide. So when plates collide, the denser plate will slide beneath the other, and the boundary between them is called a megathrust fault. So it's basically a huge fault, and it's dipping at about 10 to 20 degrees. So that's really important because it means a lot of the fault lies within the brittle outer part of the Earth. So we can have earthquakes slip over widths of maybe 100 kilometers or more. Those transform faults, because they were vertical, they can only rupture the brittle part of the Earth, so their heights might only be a couple of tens of kilometers. So these megathrust faults are much, much bigger. The location of the biggest megathrust faults on Earth are at subduction zones, where one oceanic plate subsides beneath a continental plate or another oceanic plate. And the added danger in these settings is that the shallow part of the megathrust fault is underwater. So if we have an earthquake on these structures, particularly if the rupture is very shallow, that will displace the seabed significantly, which could cause a tsunami. And it's these types of settings that the 2004 Sumatra Andaman earthquake and the 2011 Tohoku earthquake, this is where those occurred. Just for comparison, this is the fault area that ruptured in the 2004 Sumatra Andaman earthquake. It ruptured one of these megathrust faults, 1,200 kilometers long and 200 kilometers wide. And in comparison with that little fault in Greece, it's just on a completely different scale. So although subduction zones are capable of producing magnitude 9 earthquakes, that doesn't mean that they all do. And this is a really interesting figure that shows the maximum earthquake magnitude that has occurred on subduction zone segments since 1900. So some subduction zones, like the western coast of South America, Alaska, Japan, and Sumatra, have experienced great earthquakes since 1900. So that term great earthquake sounds weird. There's something great about an earthquake, but it's what we call earthquakes which are a magnitude 8 or greater, so with the orange, the red, and the purple colors. But there are subduction zones which have not experienced those very high levels of seismicity over the last 100 years. And one of those includes the Hellenic subduction zone, our closest subduction zone, where the African plate is subducting beneath Greece. We haven't seen any really large earthquakes here in the last 100 years. And I think many people that go on holiday to the Greek islands probably don't realize that the same processes are happening there as around the Pacific Ring of Fire, where we hear a lot more about earthquakes. The same goes for another nice holiday destination, the Lesser Antilles in the Caribbean. We haven't seen too much activity there. So the question is, are those subduction zones behaving in a different way? Is there something particular about the fault zone that means that rather than sticking for hundreds of years and then slipping in an earthquake, do they instead creep more silently? Is there just something fundamentally different about them? Or is it, oh no, I've crushed my biscuit, or is it simply that the last large earthquake was hundreds or thousands of years ago, and we don't have too much historical information about it? We're pretty sure that's the case for the Cascadia subduction zone, which lies along the west of North America, where it's been really quiet in terms of earthquakes on the Megathrust fault, but in 1700, a magnitude 9 occurred. So that's certainly an area of concern. So I think it's fair to say that back in the year 2000, this was kind of our view of how subduction zones behaved. We used to think that at depths of around about 10 kilometers, perhaps to about 40 kilometers, we had this zone, which is shown here in pink, where the Megathrust fault could lock up and accumulate stress. And once that stress built up and could overcome the friction between the plates, it would slip and produce a Megathrust earthquake. When you go deeper, the temperature increases, and you reach the brittle ductile transition. And at that point, the Megathrust fault can no longer sustain earthquake propagation. It can no longer crack in an earthquake. Instead, it creeps without producing earthquakes, and we call that aseismic creep, and that's shown in blue. We used to think that the shallow parts of these subduction megathrust faults were also aseismic, and we thought we couldn't propagate earthquakes through these zones. The idea was, that in these areas, the contact between the plates is really loose, and you can't accumulate stress and then have an earthquake. The yellow zones are somewhat transitional, so they're kind of partway between enabling stick-slip earthquakes and partway between being aseismic. So the idea was that we had two different types of fault slip at subduction zones, stick-slip and creep. Good. So I think that's enough background material now. So I forgot to warn you at the beginning of this lecture that there will be some audience participation. So I'm going to do now what I like to call a seismic hazard awareness exercise. So we've talked quite a lot about plate tectonics, but we haven't really talked much about seismic hazard and what you should do if you found yourself in an earthquake. We don't have big earthquakes in the UK, but it's still useful to think about this in case you do experience something when you're traveling. So what I like to do now is I'm going to put you in a situation, and I'm going to ask you to vote for what you would do by raising your hand, or feel free to act it out. I'm very happy for that to happen too. Do as you please. So the situation is, you are sitting in a cafe, this nice cafe here, in the small coastal town of Gisborne. Doesn't matter where Gisborne is, I'll show you where it is on a map a bit later, but it's on the east coast of the North Island of New Zealand. What happens next is a moment magnitude 6.8 seismic event happens on a shallow fault 15 kilometers directly beneath you. So 15 kilometers might sound quite deep, but in terms of earthquake rupture, that's actually really shallow. So this is basically a bullseye hit. So what do? I'll read out the options, and then I'll ask you to vote by raising your hand or acting. Do you do nothing? Finish your flat white coffee? Do you dive under the table and hang tight until it's all over? Do you head for high ground? Or do you run around screaming for there is no hope? Okay, option number 1. Okay, a few people. Very chilled and relaxed over in that corner. You're more relaxed than this afternoon's crowd. Option number 2. Okay, quite a few of you. It's going to be quite tight and cozy with all of you under those tables. Option number 3. Probably the majority. You've noted it's a coastal town, so you could be anticipating there could be a tsunami. And option number 4. There's always one. There's always one. I'd probably be with you. Okay, so let's now look at what did happen. So what I've got now is some stills from some CCTV camera footage that show what happened to these people and the cafe during the seismic event. So if you're of a nervous disposition, you might want to look away now. Absolutely nothing. I haven't messed my slides up here. Nobody died, no buildings fell down, nobody felt anything at all. Not only that, but none of our seismometers detected anything either. So how can this be? How can we have a moment magnitude 6.8 seismic event that goes undetected by these really sensitive instruments? So this is an example of what we now call a slow slip event or a silent earthquake. I tricked you in that quiz in that I didn't call this an earthquake. I called it a seismic event. So what happened here is that there was as much slip as a moment magnitude 6.8 earthquake, but it didn't happen in seconds like a normal earthquake producing shaking. It took place, in this case, over 4 weeks. And these slow slip events, they were first detected at subduction zones in 2002, and they've now been detected around the world, and they can take place over days, weeks, months, even years in some cases. In the case of this Gisborne slow slip event, the slip rates got up to about 0.5 centimetre per day. So that's much faster than tectonic plates creep. They creep at just a few centimetres per year, the rate your fingernails grow. 0.5 centimetre per day is much faster. It's more like the rate your tomato plants might be growing on a hot day. But it's definitely not fast enough to incite seismic waves and produce shaking. So the discovery of these slow slip events has thrown up lots of new questions. Can we consider faults which have these slow slip events, like in Gisborne, to be safe in terms of seismic hazard? Are these slow slip events good? Are they kind of releasing stress gradually, like a kind of kettle letting off steam? Or, if we have one of these slow slip events, is it actually loading and adding more stress to the fault zone around it? Could one of these slow slip events actually trigger a large earthquake? Might they actually be quite a bad thing to be happening? We've only known about them for 17 years, so that's not really a very long time window of observation to see how they interact with regular earthquakes. Bearing in mind that earthquakes at subduction zone, these megathrust earthquakes, might take place once every few hundred years. 17 years is a pathetic observation time. But there is some evidence, I've skipped ahead there, I'll go back again. There is some evidence that before the Tohoku earthquake in 2011, that there were some slow slip events in the area. This paper from 2015 suggests that in the years preceding 2011, there was slow slip in this red patch and also in this purple patch. The red to blue colours show the displacement that happened in that earthquake. I'll come back to that in a moment and just go back to this slide. So a question that you might have is, well, how do we know slow slip events happen if you can't detect them at seismometers? The reason we know they happen is because GPS stations move by as much as if a moment magnitude 6 or 7 earthquake had occurred. So everybody now is super familiar with GPS technology. It's in your smartphones. It's the thing that puts the nice blue dot on Google Maps so you can never be lost unless your phone runs out of battery, which happens to me all the time, and then you haven't printed out the maps and it ends in a disaster. But in places like New Zealand and Japan, there are really dense networks of these GPS stations set up specifically to investigate how continents deform. And this is what they look like. So the idea here is that if our downgoing plate is moving to the left, if the megathrust fault is stuck and if it's locked, then it's going to push the overriding plate left with it. It will basically kind of get a bit of a piggyback ride. And we'd expect those GPS stations to move to the left. This is some real GPS data from the Gisborne area. Along the x-axis is time. I know it's a bit difficult to read. And along the y-axis, think about this as kind of GPS location. So when the dots move down, that means the GPS station is moving from right to left. And that's what we'd expect to see if the megathrust fault is coupled, if it's locked. If we had an earthquake, we'd expect the overriding plate to now be thrown to the right. And on the GPS data, it would look something like this. What was kind of odd is when people like Laura Wallace from GNS looked at the data from since 2002, is that you have these excursions without any earthquakes happening. And that's because that movement is taking place over that 4-week period. So as I mentioned already, these slow slip events have thrown up lots of new questions. And they have also meant that our little model of subduction zone seismic behaviour is now wrong. We don't just have stick slip or creep. We now know that slip on faults is more like a spectrum, where stick slip and aseismic creep are end members, and slow slip is somewhere in between. And the more instruments we put out to investigate these events, we find other types of slow slip events that are shorter or longer in duration, and they have different rates. So actually fault slip is much more kind of on this spectrum. The other thing we now know is not correct about this model is this idea that earthquakes can never propagate to the seabed. So in the 2011 Tohoku earthquake, you'll notice that the slip contours here get really close to this line. That line is called the deformation front. It's basically where the Megathrust fault reaches the sea. And in some places, that displacement reached all the way to the seabed, and that displacement in some cases was as large as 50 meters. So not only did the earthquake propagate to the seabed, it actually involved slip of 50 meters, which is just crazy. And that's one of the reasons why this earthquake came as quite as a surprise. We weren't really expecting to get a magnitude 9 here, based on the idea that slip couldn't propagate any further than this position. So we now know that that's not correct. And also that then throws up lots of questions. Well, why could we have fault slip going all the way to the trench here? Is it something which could occur at other places? Do we now need to perhaps rethink our seismic hazard models in other areas? So subduction zone scientists are now left with the huge question of what controls how faults slip? Why do some faults fail in huge megathrust earthquakes? Why can some faults let earthquakes propagate all the way to the trench? And why can some megathrust faults allow slow slip? So scientists are now trying to address these questions using various technologies. GPS is just one. But the most direct way you could perhaps address this question is through drilling. Let's drill through these fault zones with different seismic behaviors and see what we find. Let's investigate what the physical properties are, what the processes are at work in these different zones. So fortunately, academics have the opportunity to do deep ocean drilling like this. Oh, it was going so well. I thought I'd cracked it. So IODP, the International Ocean Discovery Programme, is the world's largest research programme in earth sciences. And it's really only rivaled by the space programme in terms of its ambition. It involves 23 member countries who each pay in a subscription to join. And that allows scientists from those countries to submit proposals, to do drilling, to answer really important science questions like the one we're talking about today, and also allows scientists from those countries to join the expeditions. In the UK, we are part of what's called ECORD, which is a consortium of 14 European countries and Canada, which doesn't just provide scientists with an opportunity to sail. Every expedition we take, one or two outreach professionals too with us, who are people like school teachers or animators or journalists. So even if you're not a scientist, there could be opportunities for you to sail with IODP. There are a few different platforms that IODP operate. The Joydes Resolution is the ship at the top. This is the one that I sailed on last year. And this is really the kind of workhorse of IODP, and it's operated by the US. The Chikyu is a much bigger ship, and it can drill much deeper in more challenging environments, and that's operated by Japan. And ECORD run mission-specific platforms, which is where, if you want to drill in somewhere where these ships cannot go, like if there's lots of ice or the water depths are really shallow, they can hire in industry ships for you to do that science and that work. So over the last decade or so, IODP have been engaging in expeditions to try and address this question of what controls how faults slip. They've attempted to drill a fault zone which has large earthquakes in the Nanoscience project. They've drilled a fault which has shallow earthquake slip in JFAST. And last year, we did the Hickey experiment where we targeted slow slip zones. So for the rest of this lecture, I'm going to talk about some of these expeditions, these quite quickly, and then we'll focus on the Hickey project. So JFAST was an extremely exciting IODP expedition where they went back to the scene of the 2011 Tohoku earthquake 1 year later. So they drilled through the fault, which experienced that huge 50-meter slip, and they wanted to see what the temperatures were like, and also to try and recover some material from the fault zone itself. They were drilling in water depths of 7 kilometers, drilling down to 850 meters. What they recovered is what's shown in the photograph up here, and this is known as the miracle core. And what I have in front of me is the miracle core. It's not the real one. The real one is safely in a core repository in Japan, but this is a model which has been made by an artist And it's a really impressive recreation of what it looks like. So at the end of the lecture, I think we're going to take this into the lower library. So if you'd like to have a look at it, then please do. So this core was special in that its composition was very different to what was below and above it. And that's what you'd expect if you've drilled through the fault zone. It's going to separate two very different geological units. When you drill fault zones, you don't recover everything, unfortunately, because they're very disrupted. There's a lot, you might only get 20 to 30% core recovery. And in this case, what scientists can say is that the fault zone is at a maximum 5 meters in width, and at a minimum, it's what you see on the table in front of you. So that's pretty thin, just 5 meters, maybe between the kind of wall and maybe the end of the lectern. So a really, really thin fault zone to experience such a lot of fault slip. What was interesting about this core is that it's composed of clay, and that clay is really sheared. If you take a look at it later, you'll see it looks really scaly. These rocks have clearly had a hard time. They've been put under a lot of deformation. The core is also really rich in smectite. And smectite is extremely weak. It has a very low coefficient of friction, only 0.08, so it doesn't take much to make it slide. The other thing about smectite is that it contains a lot of water. So the idea is that as the earthquake propagated, it heated the smectite, heated the water in it, which expanded. And because smectite is very impermeable, the water didn't have anywhere to go, so it got to quite a high fluid pressure. So this combination of a high fluid pressure and very weak fault material led to the large amounts of slip that we saw in that event. So this smectite forms from altered volcanic ash. So it might be that due to the activity of volcanoes tens of millions of years ago, that's why we had this ultra-thin smectite layer, and perhaps that's why we had so much slip in this area. So a good question is, could we have similar conditions in other subduction zones around the world, or is this something quite special and quite unique? The Nanoscience project is probably the most ambitious of IODP's projects, and it's been going on for the last 11 years. The target here is not to drill a shallow fault zone like this one, it's to drill a deep fault zone in the seismogenic zone, in that pink zone that is accumulating stress and where we know earthquakes can actually nucleate. That's what we'd like to target here. The Megathrust fault here is at a depth of 5.2 kilometers, so that's very challenging. As I said, it's been going on for 11 years. They haven't drilled for 11 years. They just kind of keep going back and doing more and trying to go deeper. This year was the last phase of the Nanoscience project, and unfortunately in February this statement was released to say that they were unable to reach the primary target. The geological formations turned out to be much more challenging to drill than they thought. So the deepest they were able to get was 3.3 kilometers. So a huge amount of interesting science was done in the Nanoscience project, but we still do not have a sample of that seismogenic zone. That still eludes us. So I'm going to move on to talk about the Hickey margin, which is one of the first places where slow slip was detected at subduction zones. So the Hickey margin lies on the east coast of the North Island of New Zealand, where the Pacific plate subducts beneath the North Island. This line with the teeth on it shows you where the deformation front is, where the Megathrust fault meets the seabed. You'll notice there's another line here with teeth on it, and that's another subduction zone beneath the south of the South Island. So we've got two subduction zones here, dipping in opposite directions. So it would be the equivalent of having a subduction zone dip one way in London and a subduction zone dipping the other way in Edinburgh. So you can only imagine kind of how much twisting and deformation would be happening in that zone in between. And in the case of New Zealand, that's taken up on the Alpine fault, that transform fault that we looked at earlier. So the whole of New Zealand is at risk of earthquakes. And in the last decade, there have been quite a lot of large ones. So in 2011, there was the deadly Christchurch earthquake. And more recently, in 2016, there was the Kaikoura earthquake in this region. But what's a bit odd is that we haven't seen any really large earthquakes on the Megathrust fault itself along the Hickey margin. There have been big earthquakes in New Zealand, one that destroyed the town of Napier in the 1930s, but we think that occurred on a fault within the overriding plate, not on the Megathrust fault itself. Two of the biggest events we know of that we're pretty confident happened on the Megathrust occurred in 1947 at the locations of these yellow stars, and they were weird. So they had moment magnitudes of up to 7, which is big, but it's not huge for a megathrust, for this to be the biggest event. But they didn't cause much shaking at the coastline. Even for a moment magnitude 7, the shaking wasn't very extreme. There weren't many people living in Gisborne, this is the town that was in our exercise earlier, in the 1940s. But the people that were there reported feeling a gentle ground rolling motion that went on for over a minute and brought on seasickness in some cases. There was certainly no severe shaking. Despite that, the events were followed less than 30 minutes later by an up to 10-meter high tsunami. So these are very small earthquakes producing anomalously large tsunami. And that's really dangerous because the earthquakes don't provide you with the ground shaking warning to self-evacuate. One of the reasons these earthquakes produce such large tsunami is because they ruptured at very shallow depths of probably less than 5 kilometers. They were occurring in that blue zone that we previously thought should have been aseismic. So we need to explain how we could get such shallow rupture. We've got about 20 years of GPS recordings now along this margin, which have revealed the following picture of coupling, locking, what portions of the fault are locked in accumulating stress. The red areas show the regions that are locked, and in the south, I knew that was going to happen. So in the south, that deep locking occurs to depths of 30 to 50 kilometers. And some of the deepest, strongest locking is directly beneath the capital city of Wellington, which is a concern. So although we haven't seen any large earthquakes on this megathrust recently, paleoseismologists have looked for prehistoric evidence of large earthquakes, and they have found that in the past, magnitude 8s or greater have occurred on this margin. So it does look like they are capable of it. In the north, the picture's really different. Here, we only have coupling to very shallow depths, and a lot of the plate boundary is now aseismically creeping. The GPS data has also discovered slow slip events, and they come in 2 flavors. We have deep slow slip events in the south at depths of 30 to 50 kilometers, and they're really hard to study at those depths. The deepest we've ever drilled is 12 kilometers in a borehole in Russia, so we've got no chance at drilling into these anytime soon. But the northern Hikurangi slow slip events are much more exciting because these occur at depths of less than 2 kilometers. The other thing that makes them exciting is that they occur almost like clockwork every 18 months to 2 years. So we notoriously are nowhere near being able to predict earthquakes, but these slow slip events we can kind of forecast when the next one's going to occur, at least to a kind of 6-month window, which means that you could, and people have, deliberately made sure their instruments are out recording for when the next slow slip event occurs. And it means you wouldn't have to leave your instruments out recording for very long to get a whole slow slip cycle. So these potentially we can drill into them. But if we think about the Earth as the body, if you had something wrong inside of you, you would not immediately reach for the scalpel and start your invasive surgery. You would first do some non-invasive tests, like X-rays or ultrasounds. And we do the same in the Earth. We would not straight away go to drilling. We would first do some non-invasive tests to get some scans to see what's going on, to make sure we're drilling in exactly the right place to achieve our science question, and to make sure the drilling is safe, both for the people on board the drilling rig and also for the environment. So in the same way that we can use sound waves, this is an example of medical imaging of breast tissue using sound. We can also image below the Earth's surface using sound too, in this technique called seismic reflection imaging. And this is the area which I specialize in. So if we wanted to produce an image of what the subduction megathrust fault looked like, it's underwater, we would take a ship, and off the back of the ship, we would hang a source of sound waves. The source that we use is compressed air. So we pump air into an instrument, open some kind of gates on that instrument when we're ready. The compressed air floods into the water column, produces a large air bubble, and that pressure wave, believe it or not, travels through the water and into the rock. Where we have differences in rock properties, we get a reflection or an echo, and that gets detected by a series of underwater microphones. We determine the time it takes those reflections to reach our microphones, and it could start to build up a picture of the different rock layers beneath the Earth. This is an example from the Barham Basin in northwest Borneo that shows these kind of beautiful antiforms. Seismic data can do more than that, though, because the strength of the echo depends on how much the rock properties change. And the properties we're interested in are the density and the speed of sound through the rock layer. So if you've got big differences in those properties, you get a high amplitude reflection, and that looks like a bright red line on this diagram. If the differences are not so different, we get a low amplitude echo, and that looks like this kind of region in here. So the brightest thing you can see in this image is this horizontal feature in here, in the core of that antiform, and this is the gas-water boundary. So above it, the porosity is filled with gas, below it, the porosity is filled with water. The speed of sound through gas is very different to the speed of sound through water, so that gives us a really high amplitude echo. So this is exactly the kind of thing that the oil and gas industry are looking for when they explore for hydrocarbons. But we can take that same technology and use it to investigate subduction zones and slow slip. And we have. So this is my favorite seismic reflection profile in the world. So if this is the only seismic reflection profile you look at in your life, you are very lucky, you've seen the best one. It's 100 kilometers long, so it's about the distance between here and Birmingham, and it images down to depths of about 15 kilometers. So imagine slicing the Earth from here to Birmingham and then kind of looking at it as if you're cutting through a cake. It's really incredible. The y-axis is in time, and that's because what we actually measure is the time it takes the sound wave to go down and come back up again. If we want to convert that to depth, we need to know the speed of sound through all of those different rock layers. And that's something that we are really interested in. I'll come into that in a second. So the first thing you see is the seabed, which is shallow, and it gets deeper, up to 3.5 kilometers. The reason I love this profile is because it looks like a cartoon of a subduction zone. It's data like this, which is how we know these cartoons look like this. Over here, this is the Pacific plate, and these are sediments on the Pacific plate which haven't yet started to deform. The seabed rises here at the Taranganui Knoll Seamount, and this is an extinct volcano which is on the incoming Pacific plate. That Pacific plate is moving to the left of this diagram, and eventually the fate of that volcano will be to become subducted beneath the North Island, and it will become consumed. As the Pacific plate moves, those sediments eventually reach the deformation front, which is here, and they begin to get folded and faulted. And this triangle is called the accretionary wedge. What's important for us today is to notice this kind of diagonal line of slightly stronger reflections, which hopefully you can just about kind of see. The character of those reflections changes as we go down dip, and those reflections are the Megathrust fault itself. So that is the boundary between the Pacific plate and the Australian plate. So it's quite amazing that we can actually kind of image that. Sorry. Okay, let's try again. So in some places, the Megathrust fault doesn't really have much reflectivity at all, which means the properties of the overriding and the downgoing plate must be quite similar. There aren't so many differences in rock properties. And in 2014, which was one of the papers I put in the reading material for the lecture, we proposed an idea that in this region we might have a seamount, possibly quite similar in dimensions to this one, which has become subducted. And this also happens to be where that March 1947 tsunami earthquake where it nucleated. So our idea is that this seamount is providing a kind of locally stronger contact point, allowing us to have earthquake rupture even at depths which you wouldn't normally expect earthquakes to be able to nucleate. Further down dip, though, we've got a region of very bright reflections which are quite parallel and continuous. And this is the area where we've had maximum cumulative slow slip since 2002. So it's quite tempting to think that whatever's causing those slow slip events is related to that bright reflectivity. But as anybody who's worked with seismic data will know, the interpretation of these sections is very subjective. Different people will see different things, and people have come up with different interpretations of what's going on here. So in one idea, it's been suggested that perhaps those bright reflections are related to the presence of fluids. And at these depths of about 4 kilometers, they must be under quite high fluid pressures. That idea is somewhat supported by laboratory experiments that have found that to spontaneously generate slow slip events in the lab, you often need high fluid pressures to reduce the effective stress to allow you to have slow slip rather than stick slip behavior. Alternatively, some other laboratory models have found that another way to get slow slip is if you have frictional properties that are kind of teetering between being stick slip and being aseismic creep. And you can get that by having a mixture of lithologies. So maybe what we have here is simply just a mixture of lots of different lithologies with different frictional properties. We've always noticed these very bright reflections down here, and as the Pacific plate approaches the deformation front, the Megathrust fault is forming somewhere within this material. So some of this stuff is likely to be what's subducted in that region. So perhaps there's just something peculiar about these lithologies that give you slow slip events. So we would really like to test those hypotheses rather than just shrugging our shoulders and going, oh, okay, could be one or the other. And the most direct way to do that would be through drilling. Ideally, we would like to drill into those high amplitude reflections and see what's causing them. That zone, however, is 4 kilometers beneath the seabed. So that's, as we saw from the Nanoscience project, that's extremely challenging to drill. We do have a CHICU in with the proposal, that larger drill ship, to do that in the future. But if that happens, it's going to be many, many years in the future. I may be retired before that happens. But we think we can approach this problem in another way. So if we produced some acoustic waves and took and tried to model how fast they are moving through that zone, we might be able to build up a picture of the speed of sound through these different rock layers. In the same way that ultrasound scan we saw earlier, the colours here are the different P wave velocities, which revealed that this was an area of anomalous velocity. What we would like to do is to produce man-made acoustic signals, send them through this zone in lots of different directions, and build up a model of what the speed of sound is like, particularly in that slow slip zone. We might find that the slow slip zone is a low velocity anomaly. That's what we'd expect if there's lots of fluids here. The trouble is that won't answer the question completely. Even if we do find it's a low velocity zone, you could argue maybe there's just low velocity lithologies in this area. If we were to couple those new seismic experiments with some shallow drilling into that incoming section, we could sample these lithologies, which we think are possibly similar to this stuff. In the laboratory, we could put it under the same pressure and temperature conditions as that zone and see what the speed of sound in it is. We could even put different fluid pressures in it and test how that changes the velocity. So with those two things together, we could start to diagnose exactly what's going on in that zone. And that won't surprise you that that's exactly what we've tried to do over the last year. So the first component is the seismic data. We want to get seismic data that will allow us to make those high-resolution velocity models. So this is the NZ3D experiment, which we heard about in the introduction, and it involves 3 components. The first component was a 3D seismic reflection volume that was acquired with this ship, the Marcus Langseth. So this ship produced, I think it was 150,000 different acoustic signals, which passed through this zone. Scientists from Japan, including Ryuta Arai, who's in the audience with us today, brought 100 ocean bottom seismometers, they work at the institution JAMSTEC, to put in the footprint of that area. So this is really good because it means when the ship is producing an acoustic signal over here, it's passing through the slow slip zone and then will get detected by those ocean bottom seismometers. These are like seismometers you use on land, but they go on the seabed, which means it's really quiet down there, so the data quality is really good. The problem is, though, that some of the slow slip is happening here. In fact, quite a lot of the slow slip is in this region. And the water depths here are too shallow that we can't really put these instruments out. So a project which I led, which was funded by NERC here in the UK, was to deploy 200 seismometers in this region. So the idea now is when the ship is producing acoustic signals, they will pass through the slow slip zone and be detected by our seismometers on land. So we can begin to image in that region. So the challenge that we had was to deploy 200 of those seismometers in 3 weeks before the first shot was made by the ship. And rather annoyingly, the ship was scheduled to produce its first shot on the 3rd of January 2018. So we had to do all of this over the Christmas and New Year period. So I was not very popular with many of these people's families for taking them away for Christmas. So sorry about that. So the experiment involved over 35 different people. This is just a subset of them here. This is on our first day. We heard a bit in the introduction about kind of women in geoscience, and I think this project was a really great example Over 50% of the people helping us with the deployment were women, and all of the people with leadership roles were women. So there was me. These two people are Victoria Lane and Debbie Daly from SEIS UK. They are the technicians for all of the UK seismometers. This is Katie Jacobs, who is leading on the New Zealand side. So this was really a collaboration between the UK and New Zealand. So this is us deploying one of our stations. So we had 50 of these broadband seismometers from the UK to deploy. These involved digging a 1 meter deep hole, putting the seismometer in the bottom, and they're powered by a car battery and a solar panel. So I spent a good deal of 2017 worrying about how we were going to protect these sites from livestock. So although when you think of New Zealand, you might think sheep, in this region there are a lot of cattle and some very big bulls. So this was a really big problem. And in the end, we came up with a fencing system with some really kind of strong metal post and tensioned wire, which you can see them putting in there. We were also lucky in that we got a loan from Germany to bring 120 seismometers from there, and we deployed them at really close spacing in this region. The reason we did that is because when we did our scouting trip, we saw quite a bit of evidence of mud volcanism in the area. The landowners were reporting that their land was kind of inflating. They had to keep replacing fences every few weeks, and there were bubbling mud pools. So a few months after those instruments were taken away, I was contacted by those landowners to say a large mud volcano eruption had happened in this area. So it covered a 1.5 hectare area of land with mud in about 5 hours. Our instruments were not there. Had they been there, so at least one of them would have been covered with mud because of how closely spaced these were. But we've now got a really nice data set that will show us what the subsurface properties were like before that eruption. And I really want to go back out here now and put out some more seismometers to see how the conditions have changed. And one of our students, Charlie, is going to be working on this data from October. Very quickly before I finish, I'm just going to say a little bit about the drilling. So the other important component was not just to acquire the seismic data, but we also need to get some drilling information as well. A very important site is this one to get into that incoming section to work out what these deep lithologies are, which might be the same stuff that's now subducted. We also wanted to know if slow slip goes all the way to the seabed. We know that slow slip goes to about 2 kilometers beneath the seabed, but it might be that it actually continues along some of these splay faults. So maybe we don't actually need to drill that deep in order to sample a fault which undergoes slow slip. So what we wanted to do is drill a transect of sites. We wanted to collect geophysical logs which measure things like the P-wave velocity, the density of the rocks while they're in situ. We also wanted to collect core, like you've seen from the JFAST expedition, and we wanted to install 2 borehole observatories. So this is why we put instruments down a hole to measure things like pore pressure, fluid flow, to try and determine if slow slip actually does go all the way to the trench. So with all of those objectives, that was too much to do in a 2-month drilling project. And that's the maximum length of time they'll let scientists go to sea before we go a bit mad. So it had to be divided up into 2 expeditions, 372 and 375. And I was very fortunate to join the science party of 375. And on these expeditions, you have about 30 scientists with different roles. Some are sedimentologists, structural geologists, physical properties, geochemists. And we also have another 30 technicians, which help us use all of the equipment on the ship. And another 60 or 70 very important people who are doing things like steering the ship and drilling and cooking and cleaning and making sure everybody is happy on the ship together for 2 months. So in the interest of time, I'm just going to focus on those 2 sites, the one through the fault and then the incoming section. So when we drilled through this fault, what we found is that the hanging wall of the fault was really consolidated. There were lots of brittle fractures, the beds were really tilted, some of them were overturned. And this is what you'd expect, because these rocks have been buried at greater depths and have then been thrust up closer to the surface. When we drilled through the fault zone, we found it was an 18-meter thick zone, much wider than the Tohoku fault zone, and some parts of it, I almost got to the end without that happening. So some parts of it were brittly deformed, as you can see in this photograph with these faults, but in other areas we had much more ductile deformation with this kind of flow banding. So the fault is kind of an alteration of brittle zones, ductile zones, brittle zones, ductile zones. So the structural geologists on board are quite excited by this, and they're wondering whether this kind of mixed mode deformation might mean this is an example of a fault that can allow earthquakes to propagate in the brittle zones, but maybe it can also allow slow slip to propagate in the more ductile regions. So what we really need to know now is, can this fault undergo slow slip? Does it? So in the expedition, we deployed this borehole observatory. It's called a cork, because it's like putting a cork in a bottle. And it involves a series of instruments down the hole. We've got these 3 grey screens, one of them in the footwall, and one of them below, one of them above. And they're measuring things like pore fluid pressure, fluid flow rates, and geochemistry. And also there's a string of temperature sensors as well. The data is not streamed back to us live. It's recorded in this data logger, which looks like this. This is what it looks like before it was deployed. So when we deployed these observatories, we didn't know if they were working. But since then, Laura Wallace from GNS Science in New Zealand has gone back with a remotely operated vehicle. Effectively, it kind of sticks a USB stick in the data logger and downloads the data. And there is data, and they are working, so we're going to get some really interesting information out of these in the coming years. The lifetime of these instruments is perhaps 5 or 6 years, so we should be able to see what happens at least over 1 slow slip cycle, maybe actually over 2. And fun fact, this is now the tallest man-made feature in New Zealand. It's 400 metres tall, and the Sky Tower in Auckland is only 390. So I'm going to show you here a quick movie of the observatory as it was being deployed. This is our drill string, and this is the observatory. And those of you who were looking closely might have seen something else that happened. This will loop around again, so you'll have a chance to see it. So on the right-hand side in a moment, you'll see a squid, which despite having the entire ocean to swim in, has to smack straight into our observatory. So I have a bit of a theory about what happened to that squid, which I will share with you at the end of the presentation. So the last, oh no, nearly did it. Sorry about this. Men don't know how easy they've got it with shirts. Okay, so the last science thing I want to talk about is this site, 1520, and this is the drilling through the incoming section. What we found is really quite a large mixture of lithologies, perhaps a larger mixture than you get in other subduction zones. We had turbidites at the top. We then went into these pelagics. They were these kind of marls, calcareous mudstones, these chalks. And then at a depth of 850 meters, we really nicely called the transition to these volcaniclastics. So these volcaniclastics, in some cases, contained basalt clasts that have rolled down the side of this volcano. These volcaniclastics are really interesting because some parts of them have velocities as low as 1.7 kilometers per second. That's almost the speed of sound in water. But other parts of them have velocities up to 5 kilometers per second. So even within this lithology, we've got massively different elastic properties. So rock physics people are now going to be taking these samples and playing with them in the laboratory to see if perhaps this kind of these volcaniclastics with these really different physical properties could be what's responsible for slow slip, perhaps without the need for high fluid pressures at all. Maybe our high amplitude reflections are actually the manifestation of these differences in velocity from those volcaniclastics. So just to conclude, this is our evolving picture of how subduction zones behave. This 2D view is kind of gone. We know we actually have a whole spectrum of different slip modes between stick slip and creep. We also know that in some areas, like in Tohoku, we can have earthquake rupture all the way to the trench. And the properties of that seismogenic zone are likely to be much more variable along strike. And the 3D data that we've now collected and are going to be working on over the coming years will allow us to illuminate more about the physical properties of this region. So just before I finish, I will share with you my hypothesis of what happened to that squid. So if you take a look in the top right-hand corner, in a moment you will see a squid enter with lots of ink kind of surrounding it. There he is. And then suddenly this thing with lots of arms leaps out and grabs it. So when we first saw this, we thought it was an octopus attack. We tweeted the clip to the Monterey Bay Aquarium, who told us that they think it's a case of squid-on-squid cannibalism. So what I think has happened, I should say this was 30 minutes after the other video. So I think what's happened is our poor squid is still a little bit dazed and confused and was perhaps easy picking for this squid to eat it. So on that note, thank you very much for your attention.
Terrific. Thank you very much, Rebecca. Do we have a couple of questions? Lady in the back with the red blouse on.
Hi, I'm actually from New Zealand and have heard about the subduction zone. In terms of hazard, what might happen? Like, because you said with Japan it's caused a tsunami. Is that kind of a similar outcome you think could potentially happen for us?
So in New Zealand, we know we can get tsunami in that Gisborne area where we had those kind of small earthquakes that produced the anomalously large tsunami. But the big question is, could that margin ever rupture in a large magnitude 8 or magnitude 9 earthquake? So probably the best people that are getting to that question are the paleoseismologists. So people that are looking for kind of old tsunami deposits over a wide region across the North Island and the tip of the South Island. That might mean that in the past, a really big magnitude 8 or 9 happened, which produced that tsunami. And as I said, they have now found evidence of at least a kind of magnitude 8 or greater. So it does seem like this is a margin where that's possible. In terms of that coupling patch, we do have that area that looks like it's really locked. And that's a region which, seismic hazard people are concerned about, particularly because the Kaikoura earthquake was quite close by. There have been a number of earthquakes in Wellington as well recently. So what that's doing to that patch it is something which is being studied. But the big question is, even if it ruptured that patch, could it actually rupture the patch with the slow slip events? That's an open question. Whether, if an earthquake nucleated somewhere else, could it rip through that region where we had slow slip, or would it stop there? That's going to be the difference between, whether you have a big earthquake or whether it could really be a great earthquake. If that answers your question.
We have another question. All right. Well, I'm sure there will be more questions when we take the core replica is going to be out in the library, in the lower library. So we'll migrate through there very shortly. But first, you can just say, so I am a geologist, but you can tell by my grey hair that I actually grew up with the kind of old-fashioned 2D model of subduction zones up in the top of the slide there. And actually, one of the great things about my job is that every now and again, we bring a lecturer in who kind of completely transforms my understanding what I was taught 30 years ago. And you've been a great example of that tonight. And also, I'm left with the impression it's very much work in progress.
It's very new. So, I mean, even many undergraduates probably don't get taught this stuff. It hasn't really migrated into the syllabus yet. So it's, very fresh and very in progress.
Yeah, fantastic. So I'm sure I'm not the only person in the room who's had a kind of subduction zone system reboot this evening, and it's been terrific. And you presented it to us in such a kind of energising way, despite the best efforts of our audio system to scupper you. You managed to get through to the end, so thank you very much again, Rebecca. We're going to take this core replica through, so if any of you have any questions you've thought of in the last 30 seconds or so, please do have a word with Rebecca out there in the lower library. But can we just express our thanks once again for a terrific talk. Thank you very much.